Example 7.14. I'm reading the question. The cord of negligible mass is wound round the rim of a flywheel of mass 20 kg and radius 20 centimeters. A steady pull of 20 newtons is applied on the cord as shown in the figure 7.35. The flywheel is mounted on a horizontal axis with frictionless bearings. Then compute question A. Compute the angular acceleration of the wheel. B. Find the work done by the pull when 2 meters of the cord is unwound. Then C is found also the kinetic energy of the wheel at this point. Assume that wheel starts from rest. Then D, compare answers to parts B and C. According to the question, okay, so a cord of negligible mass is wound round the rim of a flywheel of mass 20 kg. Okay, so then is a one cord so of negligible mass is wounded round the rim of the flywheel. So flywheels, it is looks like a CD. I will upload one video about the flywheel in our channel. So look at there how flywheel is there and how we are doing the experiment with the flywheels. Okay, so don't forget to watch that uh, flywheel, or you can also search in the YouTube, you can find it also. Okay, so from that, so here it is looks like a one CD type of one body is there, and middle of the CD, that is center of the CD, one axis is one axle is passing, and that we called here like a, it is one of the best example like our flywheel. Okay, so the mass of the flywheel is given here, mass of the flywheel, that is 20 kg. Okay, mass m is equal to 20 kg. Okay, and radius, so radius of the flywheel is also given, that is capital R is equal to 20 centimeters. So just convert this is into meters, that is 20 into 10 to the power of minus 2 meters, and that is equal to um, 0.2 meters. Then also provided a steady pull of 20 newtons. Pull means here force. That force is equal to 20 newton. It is a constant force. Steady force means constant force. Then uh, applied on the card is shown the figure. The flywheel is mounted on a horizontal axle with frictionless bearings. Then compute the angular acceleration of the wheel. Okay, so the angular acceleration alpha is equal to how much? This is our first question. A is equal to angular acceleration alpha is equal to how much? We know that alpha formula, that is alpha is equal to omega minus omega naught by t. But here in this uh, omega is not given and omega naught also not given, so that's why we can't use this formula, and also time is also not there, so we will use another formula. Okay, so for that I am taking one formula, that is tau is equal to I alpha. Okay, tau is equal to I alpha. Tau is the angular force, that is moment of force, and I is the moment of inertia, alpha is the angular acceleration. Okay, so here tau means, it is our diagram is like this given. Okay, this is our flywheel, it is like this, and here this is the axle, actually it is like CD type, and this is our force, that is force F is equal to 20 uh, newtons. Okay, 20 newtons we are applied, sorry, 25 newtons. I written wrong here. This is 25 newtons and this is 25 newtons. Okay, and this is the radius of the flywheel. Okay, so this radius. Okay, then when we are applying this force here, then it is axial and our flywheel is like this CD. Okay, the CD is rotating like this, like that flywheel is also rotating. Okay, then this is R and this is our force. Then here when it is rotating, it is having the rotational motion. That's why because of the this force, it is because of the torque, it is rotating. So that's why there is a some torque. The torque tau is equal to, already we know that torque tau is equal to Ref sin theta, but theta here between these two 90 degrees, so that's why tau is equal to Rf. So we have a R, radius of the flywheel, that is equal to 0.2 meters, and force applied here 25 newtons. So we got the tau. Then I, this I is moment of inertia. We all know that, that is mr square for single particle. But it is not a single particle. It is the one like what, flywheel. Okay. So for flywheel, it is equal to mr square by 2. Okay, so moment of inertia of a flywheel, that is equal to mr square 2. So moment of inertia is different for the different bodies. Already we have a one tabular form in the textbook, you can watch there. Okay, so for y flywheel, I is equal to mr square by 2. Then we have a m and r, then we can calculate the I, and rf, from that we calculate the tau. Then we substitute here and we got the angular acceleration. So first I am taking here torque tau is equal to F into R, or R into F. So force is given, that is equal to 25 into, and R is equal to 0.2. Okay, so if we solving this one, and we got that is equal to 25 into 2, 0.2, that is equal to 5 Newton meter. This is what our torque tau. Then find out the moment of inertia for flywheel, that is mr square by 2. Okay, so mass of the flywheel, that is 20 kg, into r, radius is 0.2 whole square by 2. Okay, so 2 ones are 2 tens are, that is equal to 10 into 0.2 means, that is 0.04, 0.02 whole square, and it is equal to, so 110 and 1 point is cancelled, that is equal to 0.4 kg meter square. This is our moment of inertia of the flywheel. Then substitute these two values in this equation, we got the alpha, that is tau is equal to I alpha. From that, alpha is equal to tau by I, and that is equal to, tau is equal to, that is 5 by, this is 0.4, and that is equal to, so if we are removing the point, that is becomes 50, and 50 by 4, that is equal to 12.4, sorry, 12.5 alpha, so that is radians per second square. This is what our first question, alpha, pick angular acceleration. Then second question, what is the second question? Find the work done by the pull when 2 meters of the cord is unwound. Okay, 2 meters of the cord is nothing but, so we take the one cord and we are using one thread, then the thread we are rotating for this. Okay, so then after pulling this 25 newtons, then this flywheel is rotating, and the which is we rotated here, the thread is opening up to 2 meters. Okay, so this total thread we are rolling, not rotating, it is rolling on this axle, but after pulling, when flywheel is rotating like this and the thread is opening up to 2 meters, then if what is the work done by that pull 25 newtons. Okay, so we all know that work done W is equal to F into S. Okay, so that is W is equal to F 25 newtons, and after applying this 25 newtons, this is opening up to 2 meters of length. That is nothing but displacement. So it is equal to 25 into 2, that is 50 joules. This is the work done. And this is our question B. And this is question 3. What is the question 3 here? Find also kinetic energy of the wheel at this point. Assume that wheel starts from the rest. Okay. Now this wheel, it is started from the rest, means it is a when after rolling the thread, we are fixed there and it is at rest, and we push it. After pushing it, it is started, means before pushing that thread, it is at rest. So that's why initial angular velocity is 0. Okay, then after pushing it by this force, then it is rotating here about the axle. Okay, so then while it is rotating, it is having some angular velocity. When it is having angular velocity, it is also having kinetic energy, that is kinetic energy of rotational motion, that is half into I into omega square. Okay, I already is there, we calculated here, that is 0.4 kg per meter square. Now we have to find out the omega. Okay, this is final omega, because here it is initially it is at rest. So then by using the kinematical equations, we can find out the omega square. That is, we have a one third kinematical equation, that is omega square minus omega naught square is equal to 2 into alpha into theta. Okay, so from that, omega square is omega square minus, this is omega naught is 0 and it is equal to 2. Alpha already here, this is 12.5 into theta is also not given. Here theta means, so angular displacement. What is the angular displacement here? For suppose after winding the total thread on this, okay, so it is some of the rotations. Okay, we are rolling that thread around this axle, means one uh, angular displacement, that is what we called displacement, that is theta. Okay, so one angle for one rotation, it is makes 2 pi radians of 2 pi is nothing but here angular displacement, like that. So the total thread which is opening, that is equal to here what theta. Okay, if we are taking one what, so for suppose anything we can use here. Yes, 1 minute please. For suppose it is rotating like this. Okay, we are using our thread is like this opening. Okay, like this kind of windings. Okay, so then it is like this. When we are pulling by 25 newtons of force, it is opening like this. Before opening, it is make some angle here. Okay, so this is nothing but here theta, angular displacement. This total, it is equal to angular displacement. Okay, so this angular displacement we can write here, that is by theta, the theta is equal to we have a formula, that is what arc length by radius. Okay, so then arc length is nothing but here how much it is opened, that is arc length. That is already mentioned in the previous question, it is opening up to 2 meters. Okay, so that is theta is equal to arc length is 2 meters and the radius of the um, flywheel. Okay, that radius of the flywheel is given by the that is how much, that is 0.2 meters here. Okay, this is 0.2 meters. So from that, theta is equal to, we can get this is 0.2 means it is 20 by 2, and that is equal to 10 radians. Okay, this is what our theta. So once again I will tell you here. So we are winding a thread like this. Okay, this kind we are winding. Okay, then when we are pulling, so this winding is nothing but, so one rotation here, it is nothing but like a one rotation. Okay, so if we are opening, this is, if you are opening, this is, while opening like this, when it is completed one revolution, that is nothing but theta. So the theta we can calculate how much it is opened and what is the radius of the this one. Okay, like that. Here we have a flywheel. Okay, this radius of the flywheel, and how much that uh, thread is opening. Okay, so you can understand by watching the flywheel. Okay, so here, then theta is equal to, we got here 10 radians. Then write down here, it is equal to 2 into 12.5 into theta is equal to 10. So this is how much, omega square. Okay, omega, this is totally 0, then omega square is equal to 12.5 into 2, that is equal to 50. So 50 into 10, sorry, 12.5 into 2, that is 25. 25 into 10. Okay, so okay, omega square is equal to, that is 250. 25 into 10 is 250. Okay, so if omega square is equal to 250, then substitute here. Okay, that is kinetic energy is equal to, this is half into I is equal to how much, that is 0.4. This is 0.4 into omega square. Omega square is equal to 250. Okay, and it is equal to, that is 2 ones are, this is 2, sorry, this point and this 0 cancel, 2 ones are, this is 2 twos are, and this is 2 into 25, that is equal to 50 joules. So kinetic energy is equal to 50 energy, sorry, 50 joules. Okay, this is the energy of the flywheel. Then compute answers to parts B and part C. Okay, for parts B, this is linear work done. Okay, by linear force, the work done is 50 joules, and by the angular uh, acceleration, angular velocity, the kinetic energy we got, that is, it is also 50 joules. Means, according to work energy principle, whatever the work done, that is equal to change in kinetic energy. Change in kinetic energy means initially there is no kinetic energy because there is no angular velocity, but we know this is final kinetic energy. Okay, so this, whatever the work done, this work done totally converted into sorry, this work done is equal to change in kinetic energy. So in this case, whatever the work done is there, and this is also equal to work done. So same work is done in the place, in the case of B and C.